Hello and welcome back. This is the webinar, Introduction to Intensive Longitudinal Methods, Design and Analysis, sponsored by SAMSI. And this is part 2 of the webinar. We left off leading into coverage of the basic multi-level model, which is the workhorse model for these kinds of data. And we're going to apply the multi-level model to an example data set where we're interested in modeling a within-person process involving a continuous outcome. So we will get right into it. So to explain the example, imagine we have a data set of 66 women who reported whether or not they had an argument with their significant other, with their partner, every day for 28 days, consecutive days. So they provide report of arguments, and they also provide a rating of intimacy on a scale from 0 to 10. And you can imagine that these women happen to be in cohabiting relationships with an intimate partner. So, the idea is that they're asked, looking back over the day at the end of the evening, imagine, looking back over the day, did you have an argument? Did you have a conflict with your partner, yes or no? So we made that a dichotomous predictor. And we also asked them, how intimate are you feeling with your partner at this moment in time? So that's the key outcome. And imagine that in addition to the 28 days of daily diaries that they did, they also completed an online background questionnaire. And in that questionnaire, you might imagine that we can collect data that reflect time invariant covariates, so things that are measured only at one time that we either believe don't change over time or that are demographics about the participants. Okay, so that gives you an idea of the example. And then the research questions related to this example are as follows. So first, we'd like to characterize how much do daily conflicts lower intimacy for the typical person. Okay. So this question is one where we have to really think about at what level of analysis are we interested in, within person or between person. And that's because intimacy will vary from day to day, as it does in relationships. But it will also vary from person to person. That is, some people just experience more intimacy than other people. But that's also the case for daily conflicts. So even though a conflict can happen on a day or not happen on a particular day, there's some people who report just more conflicts over the 28-day recording period, right? And some people report less. And in this sample, actually, there's some people none, right? But what we're interested in is, regardless of whether you're a higher conflict person or lower conflict person, or a higher intimacy person or lower intimacy person, on a day where you experience a conflict and report having a conflict, compared to a day that you don't have a conflict, is there a difference in the level of intimacy between those two types of days? Right? And we can characterize what that association is for the typical person. Now, phenomenologically, right, I think theoretically, I would say that conflicts cause people to experience less intimacy. And so that's a causal process that we're trying to model. Now I know we often get nervous about using the term cause here, or cause when it comes to any kind of observational data like there is in this case. But there's certain assumptions that when considered bolster, right, an inference, a causal inference. And we'll talk a little later about some of these assumptions. But one of the important aspects that is necessary is that, is there a plausible mechanism that would explain why conflicts would lower intimacy? And I think there is from the relationship literature. And we also have a design that allows us to look at this relationship within person and take into account the between person association, which is not as important as the within person association in this context. If you're going to go through the bother of collecting longitudinal data from individuals, you're going to want to examine the within person association for sure. But we'll also get the between person association as well. This analysis will produce both. So the first question, like I said, is how much do conflicts lower intimacy for the typical person? Okay. And we're going to be focused on the within person association between daily conflicts and daily intimacy. And then how much do people differ in this relationship? Right, so the idea is that while there might be an effect of conflict on intimacy for the typical person, for some people that effect may be smaller, for some people that effect may be larger. And can we characterize this variability, this between person heterogeneity in this effect? And then after characterizing this heterogeneity, we can then try to model it. And the question related to that aspect is, does relationship quality, a variable that we've measured once and is a variable that represents a person's global positive or negative evaluation of their relationship, so does relationship quality buffer daily conflict reactivity such that those with higher relationship quality are less reactive to conflict? So that's a key research question. And it's a research question that reflects a cross-level interaction because, again, the key outcome is intimacy, but we're interested in the within-person variability in intimacy and linking that to within-person variability in conflict. But then we want to see if that relationship depends, or the size of that relationship depends on whether you're in a high or low quality relationship. So those are the research questions for this example. Here are the variables. We have a participant ID. We're going to have a variable that indexes time, which is basically diary days, 0 to 27 for the 28 days. We're going to put time into a different metric. And this transformation doesn't actually change the association between time and the outcome variable at all. It just will change the size of the coefficient. And remember when we talked about centering, or knowing where the 0 is on all your predictors, we want to put 0 in the middle of the 4-week period, which is basically, in between weeks 2 and 3 of this 4-week period. That's because we're not expecting there to necessarily be any kind of sort of growth or systematic change in intimacy over the 28 days. What we're really interested in is the fluctuations from day to day in intimacy and trying to explain those. So what we do is we take time, we center it, and we divide by 27 to be able to get time in the units of 1 week, and that variable itself will be centered. Okay, intimacy is our key outcome variable, and it varies from day to day and ranges from 0 to 10. Conflict is our key dichotomous predictor, measured every day, and is 0 if women say that they didn't have a conflict, and 1 if they did have a conflict that day. And then relationship quality has been coded such that there's a cutoff where below that cutoff, people are in a low quality, are placed in the group that indicates being in a low quality relationship, and one is where they're in a high quality relationship. Now, let me just say that for pedagogical purposes, we're making the predictors dichotomous, but they don't have to be. And in fact, one can argue that the severity of conflicts can differ from each other, and that you'd want to make this continuous, and that relationship quality is a dimensional variable, and you'd want to make that continuous. But we are doing this for pedagogical reasons, okay, for this example. So we are aware of the fact that we don't necessarily want to dichotomize something that is continuous in its nature. So there's a data set in SPSS that you can get from the course website, from the book website, intensivlongitudinal.com. It's a chapter 5 example data set. And here we have ID, and we have time going from 0 to 27. Time 7C is the centered version, centered on the middle day, which is right about here. Intimacy is our key outcome, varies from day to day. Conflict is our key predictor. And then these columns here are steps in showing one way of doing the separation of within and between person variability in daily conflict. Okay, and we will get to talking about that in a little bit more detail. And then finally, the last column, relationship quality, which is a time invariant covariate as compared to conflict, which is a time variant covariate. So relationship quality will be either 0, 1 for all the days for a particular woman. So this is our example data set. Okay, getting to this issue of within versus between effects of time varying predictors, we're going to need to separate the within person from the between person effect of any longitudinal predictors, and especially in an observational context where there's no manipulation. And so we're expecting that people are going to vary both within person on conflict. That is, that they'll have some conflict days and some no conflict days, but also people will differ from each other in the average amount of conflict, which basically will represent, a ratio, because it's going to be the number of conflicts, the number of days that are reported of conflict over 28, because that's the total number of days. So basically, the average is going to be, a fraction or a percentage out of 100%, which would be the total number of days, 28. So we can think of an individual's daily report of conflict as fluctuating around whatever that person's average number of conflicts is, right? So we can calculate that average for each person, and we can think of the daily report of conflict as fluctuating around that average. But we can also envision this average differing from person to person, right? And notice that we're focusing on the predictor, daily conflict, not so much intimacy, although intimacy also is a variable that varies from day to day and from person to person. But like we mentioned earlier, multi-level models already handle the variance decomposition of within and between variability in the outcome. That's actually sort of an automatic thing in multi-level models. Once you put in a y into the model, even if you put no predictors, the sort of unconditional model, essentially, no predictors of y, is essentially a model that separates the within-person variability in y from the between-person variability in y, and also gives you a mean, an intercept, which with no predictors is the mean. So multi-level models already do the separation in the outcome, but we have to somehow take into account the fact that there is this, that people will differ on average in terms of their average conflict. People will differ in terms of average levels of the time varying predictor. So in essence, daily intimacy, which is our outcome, has both within and between person variability. Daily conflict also has both within and between person variability. And we want to somehow take into account mean conflict, either, and a common way of doing that is subtracting it out, which is a form of person mean centering. But we want to account for the fact that people will differ in mean conflict, and taking that into account then allows us to extract what might be called a pure within-person interpretation of the effect of daily conflict on daily intimacy. So just because these are variables that vary from day to day and we look at how they're associated, doesn't mean that we're looking at a within-person association or within-person effect. We have to make sure that we have taken into account the between-person relationship between daily conflict and daily intimacy. So here, this next slide here is a depiction of basically two ways of doing hand calculations. And there are more sophisticated ways of doing this kind of person mean centering. And in fact, in one program, M+, there's a latent version that actually is a better option, technically speaking. But for the purposes of this introduction, I think it's useful to be able to go through the exercise of doing the separation of within and between essentially by hand, so that you can really see what's going on. So here's our raw collected conflict variable that's 0, 1. And notice that, here is a day where there's a conflict for this woman. Here's another day on day 15. And there may be other days we can't see all the way down to 28. Okay, day 28 or it would be, day 27 on a 0 to 27 scale. So what we want to do is we want to take the variability in conflict, and we want to separate the within variance from the between person variance in that variable. And so this is one set of steps to be able to do that. So essentially the first step is we do grand mean centering. So it turns out that the average across all the days for all the people is 0.221, basically 22% of all 1,648 days, I believe, which would be 66 times 28. 22% of those days are conflict days, days where conflict equals 1. And the remaining 78% are no conflict days, which are days where conflict equals 0. And so the first step here is to do grand mean centering by calculating that single mean, that grand mean across all days and all people, and subtracting it from conflict. And then this is what we get, right? We end up with the zero conflict days being negative 0.221, and the positive or the conflict days being 0.779. Okay. Now, the difference between those two is still 1 unit, but because this variable is centered, it looks a little funny in this way, but it's still 1 unit difference between a no conflict day and a conflict day. Now, we're going to take this variable conf C and we're going to calculate the person means, because people are going to differ in their average amount of conflict. Now, this number looks a little funny, negative 0.114, but what it is it's negative because because the averages, the person means, the person averages were taken from a variable that itself was centered. And so the fact that this is negative is saying that this woman's average number of conflicts, average amount of conflict across the 28 days is lower than average. You know, there's some women's means who are going to be below 0, and other women's means are going to be above 0, essentially, because this is a centered variable, that this is coming from a centered variable. But the important thing to point out is that this is a variable that only varies from woman to woman. We can't see woman 2 and woman 3 below here, but all the rows for woman 1 are going to be the same score because there is no within person variability in this variable. And this variable has been labeled conf CB, where basically it's conflict centered, grand mean centered, but then it's the between person part only of this grand mean centered conflict. And then what we do is we take conf C and subtract, which is the centered, grand mean centered variable, and we subtract from it the person means, which results in a variable that we're calling conf CW, which is basically grand mean centered conflict, but then the within person variability, the variability only is contained in this conf CW variable. So notice that this variable will vary from day to day in terms of when conflict occurs versus not. So notice that for this woman, this particular woman, a no conflict day is a negative 0.107, and a conflict day's value is 0.893. But the difference between a no conflict day and conflict day is still 1 unit. It's still 1, just like it was in the raw variable. But we can think of these fluctuations, if we will, being around this woman's average, which is this value. Okay, so this is one set of steps to be able to take the raw conflict variable and create the between person part that has only between person variability and conflict, and the within person part, which has only within person variability, daily conflict. There's another set of steps that we can get the exact same result. It just does it in a different order. So, this second set, but we result in the same 2 columns that have the same values. Okay, so we start with raw conflict, and then we just calculate from this raw conflict the person means of conflict. Okay, so we person mean conflict, and then we center these person means. That's the second step. We center these person means, and we get conf BC, which is the between person part of conflict, but itself has been centered. Notice this results in the same exact column here as conf CB. And then what we do is we take the original raw conflict variable, subtract conf B, And what we get is conf W, which is the within person variability in conflict that's contained. So this variable contains only within person variability, and that's exactly the same as the conf CW variable. Okay, these are just two different ways of getting to the same place. The important thing is that we're separating within from between person variability in daily conflict. Okay. So what that means is when we put these two variables into the model, we're going to get a coefficient that will index the within person association between conflict and intimacy. And we're going to get a separate coefficient that will index the between person association between conflict and intimacy. And that reflects our desire covering the fundamental issues. The one that said it's important to separate within and between person effects. Right? If we had just put in this raw variable of conflict, we could have put it in raw, or we could have put it in grand mean centered, which this is just a linear transformation of each other. If we had put in either of those, we would get a single coefficient that would be essentially a blend of the between person association and the within person association. And if those associations are not the same, or if they happen to be different signs, then the coefficient that we get for the single conflict variable is going to be biased. It's going to be confounding within and between person variability and conflict. So we're separating this out so that between can have its own effect, within can have its own effect. Okay, so let me step back here and just point out that, notice that we did both grand mean centering, and then we also did group mean centering. So we did both, actually, and both are options at when you have variables that vary, that are time varying, predictors that are time varying. And these are so-called level 1 predictors, right? Level 2 predictors would be the variables that don't vary, time invariant predictors like relationship quality. Okay, so remember that W is our symbol for the time invariant predictors. And so these predictors at the between person level or at level 2, there are only two options for centering. One is that we don't center, we put it in raw. And in this case, that would be okay because we know what 0 means. 0 has a clear meaning. 0 are the women who are in low quality relationships with their intimate partners, right? And 1 are the women who represent the women who are in high quality relationships. So that's one option. Another option is that we could center W, and the only mean that we can center around is its grand mean. And it turns out that either of these are fine, but we're going to leave it in its raw form because 0 has a meaning. So it's a dummy code, essentially. And so here's the process data set with the symbols that are going to correspond to the multi-level equations that we're going to be going through in just a little bit. Okay, but this is sort of a bird's eye view of the entire data set. I should just note that the brev symbol, which looks like a C kind of laying down on its side, that's referring to centering. Okay, that's referring to centering, and in particular, grand mean centering. Okay, but when we take that grand mean centered Xij variable and subtract from it the person means, which is this variable here, X dot J, so averaging across the days for each woman J, when we do that subtraction, This represents person mean centering. Okay, I think it's always a good idea with these kinds of intensive longitudinal designs that before you launch into data analysis, that you look at panel plots, where basically you plot your outcome and your predictor by time, and you do it for each person or each unit in your sample. So here, this next slide is the intimacy outcome going from 0 to 10 on the y-axis, and then 28 days on the x-axis. And the top panel are the women in the low quality relationships, and the bottom panel are the women in the high quality relationships. And there's a few things that jump out at me when I look at this slide. First of all, there's a lot of within-person scatter for the women, both in the low and the high quality relationships. Okay. A lot of within-person scatter. For some women, the scatter may not be as big. For some women, it may be quite big. Okay. Here's a woman where there's quite a bit of scatter. And that's what we're interested in modeling. We're interested in modeling those ups and downs, right, which reflect within-person variability. Okay. Now, the other thing to point out is if you squint really hard, you might sort of see that the women in the low quality relationships also their intimacy levels tend to be a bit lower. Their averages across all the days tend to be a bit lower than the ones for high quality relationships. That may not be that surprising. The other thing to notice is that there don't seem to be any systematic time trends, right? So there doesn't seem to be evidence that there's some women who are going up over the course of the 28 days or going down over the course of the 28 days or showing a quadratic trend or some other kind of systematic trend over time. So seeing that, we might not expect there to be much of an effect going on with time, either on average or reflecting any variability from person to person in terms of the effect of time. Okay, so this is the entire data set in terms of the outcome that we're seeing here, all in one slide. And I think it's useful to do this because you want to make sure if there is a time trend that you're capturing the functional form of that time trend. That's important to do before you start modeling the within-person fluctuations around the time trend. But here, there really is no time trend, it turns out. The other thing is that this view can also allow you to pick up any data entry errors or data coding errors. Like basically, are there values that go below 0 and above 10? Are there missing data? And we can see that in this data set, there are no missing data for these 66 women. Everybody has 28 days. We'd also be able to pick up if there were some women who showed no variability, and how many of those women show no variability, because if that were the case, then it would make it harder for us to find relationships between daily conflict and intimacy at the within-person level. This next slide does the same panel plotting, but for our key predictor daily conflict. Low relationship quality panel, high relationship quality panel, and on the x-axis 0 to 28, on the y-axis basically 0 and 1, right? So the thing to notice is that there's quite a few women with a decent amount of variability, right? The women with the sort of tables or these mesas here, plateaus, I guess, would represent consecutive days of conflict, like here or like here. Okay. I guess the thing to notice is that there's some women who have no conflict. Here's one woman that has no conflict. Here's another woman that has no conflict. Here is another woman that has no conflict. Here's another one that has no conflict. And there are some women who only have one or two conflicts, right? Like here and here. Okay. Again, this is a bird's eye view of our daily predictor. And there does seem to be a decent amount of variability to allow us to be able to examine the within-person association between conflict and daily intimacy. Okay, this slide are the equations for the multi-level model. Here in the multi-level, level 1, level 2 representation, and also in the equivalent mixed model representation. But let's start with the level 1, level 2 representation. I think this is useful to see in this form. So the level 1 equation is a person-specific equation. So it's predicting intimacy, or Y, at a particular time point for a particular woman, J. Okay. We're going to have an intercept that's going to vary only from woman to woman, J. Okay. So that's what beta 0J represents. And we can imagine that we have 66 of these. Basically, there's a distribution. That there's going to be a distribution of these that we're going to then model themselves at level 2. But let's just start with pointing out that this is beta 0J varying from woman 1 to 66. Beta 1J also potentially varying from woman 1 to 66. And this slope is indexing the linear relationship between our person mean deviated X, which represents only within person variability and conflict. How do I know that? Well, we're starting here with Xij, which has been grand mean centered. X dot J represents the person means, so averaging over the days I, and then this varies only from person to person, J, and that has been centered, those person means. And this quantity represents the deviations of the person means from each woman's daily score on conflict. So this is the within person, this variable represents within person variability in daily conflict. And beta 1J potentially allows each woman to have a different relationship between daily conflict and intimacy. Okay. Beta 2J allows there, again, to also potentially be a different relationship between time and intimacy. Time varies from woman to woman and day to day. However, in some ways, we could just have time be TJ or TI, because really it's the same for all the women, right? So it's exactly the same variable. And it's been centered in the middle. So in days, the 0 point is right at the middle of the 28 days. And then there's a within person residual, EIJ. We'll talk about some of the assumptions about the residuals a little bit later, but this is all the variability, or these are the deviations from the actual Y scores after taking into account the predictors for each person. Okay. Now, because each of these coefficients can potentially vary from person to person, at level 2, those coefficients are then modeled themselves. So we have equations for each of these parameters that can potentially vary from person to person. So the beta 0J, and there you can think of it as there being 66 of them, those beta 0Js, they're modeled itself, they themselves are modeled with an intercept and with a slope indexing the effect of being in a high versus low quality relationship, which is W sub J, varies only from woman to woman J. Okay. So if this is the effect of being in a high quality relationship, this intercept pertains to the women in a low quality relationship. And then this effect is the difference between high and low. Okay. Gamma 0,2 is the coefficient associated with the person means of conflict. That's the exact same means as up here, subtracted out of the daily scores, but then put back in here. So with its own coefficient. So this is going to represent the between person effect of conflict and intimacy. Okay. And then this third coefficient is an interaction between relationship quality, our WJ variable, and the person needs on conflict. It's an interaction. It's a within level interaction. So it's an interaction between two between person variables. And the purpose of this really is to show you that this is possible. We can look at interactions within any of these level 2, between the variables in any of these level 2 equations. Okay, we may not be interested in this question, but it is possible. I guess if we were interested in it, this would basically say, does the between person effect of conflict on intimacy depend on whether you're in a high or low quality relationship? That's essentially what this would mean. Okay, and then there's a residual, U0J. So this is a person specific residual, while this is a residual that is unique to each time point for each person. This is a residual that is associated with what's unexplained in the beta 0Js, which essentially represents residual variance, residual between person variance in these intercepts. That's not explained by what is in the model. Beta 1J, we take from up here, has its own level 2 equation. Okay. Gamma 10 represents essentially the average of this slope, of the slopes here, the average for the women in the low quality relationship group. While gamma 11 represents the difference in this association between daily conflict, within person part of daily conflict, and intimacy. This would be the coefficient for the average for the women in the low relationship quality group, and gamma 11 would be the test of the difference in that coefficient for the women in the high quality relationship group versus the low quality relationship group. Okay. This is a cross-level interaction. This is a cross-level interaction because what it is we're seeing that the relationship between daily conflict and intimacy, that within-person relationship, does it depend on whether you're in a low or high-quality relationship? So this is a cross-level interaction. And then U1J is residual variability, residual variance, residual between person variability in the beta 1Js. Okay. So that's allowing then for both the low and the high relationship quality women, allowing their slopes to vary. That's what U1J means. U0J is allowing the intercepts to vary for both the low and high quality relationship women. And then beta 2J has also its own equation. Notice that there's just a gamma 20. There's no U term here, which means that we're not estimating a random effect, or we're not estimating between person variability in this average association between time, and in this case it's linear. This is a, this is a linear, represents linear time, and y sub ij, intimacy. Okay. We could have included u2j, which is what that symbol would have been. However, going back and looking at the trajectories here, you can see that there really isn't any evidence of systematic change over time, or individual differences in systematic change over time. So what we've done is we included just the fixed effect of time. Now, there is an equivalent representation of these level 1, level 2 equations called the mixed model, which essentially what you do is for beta 0j, you substitute everything on the right-hand side of that level 2 equation. So you substitute all of this into beta 0j, you substitute what's on the right-hand side of the equation for the beta 1j term, you substitute what's on the right-hand side of the equation for the beta 2j term. And what you get is what you get down here. So right here, these are the terms that were on the right-hand side of the beta 0j, excuse me. Here are the terms that were, these two terms here are the terms that are on the right-hand side of beta 1j. And then this is the time term that's here. U0j represents a between-person variability in, a residual between-person variability in the intercepts, and that's a between-person random effect. U1j is a between-person variability in the slopes, and that's the within-person slope. And then EIJ is a within-person residual. Varies from time point to time point and person to person. Okay. One thing I want to point out is one of the reasons why it's useful to understand the mixed model form of this equation is because, or the multi-level model form, excuse me, of this model versus the mixed model form, is that, and I get this from some people. Some people ask, like, why is this called gamma 02? But then this is called gamma 20, and why is this called gamma 01? And why? And then, but this is called gamma 11. Like, what's going on there? How do you know what's the rationale for how these are labeled? Well, the multi-level representation shows that to you, because basically the first 0 represents, the 0th term, which is usually the intercept, the first term, which is the first slope, the second term, the second slope, and so on. That's the first 0. And then the second 0 tells you the number term in that level 2 equation. So this is the gamma 0. All of the gammas in this level are going to start with 0 because we're referring to the 0th term in the level 1 equation. And then the 0th term of this first level 2 equation is going to be the intercept, or the grand intercept, if you will. And gamma 01 then is referring to the first term in the first term in the first level 2 equation. Gamma 02 is the second term. Well, it's really the third term, but it's the second slope. And then gamma 03 and so on. So that's why these have these subscripts, is if you understand the labeling here in this multi-level representation. The other thing to notice is that sometimes people get the impression that these beta 0j's are actually estimated, and they're not technically estimated. These you can really think of as realizations from the model. That is that we can ask the model to generate estimates of each person's intercept and each person's slope for the within person effect, and for each person's potentially for each person's time effect, but we haven't actually estimated the residual, the between person variance for that term. But it's not these, though, that are estimated. We can ask the model to give us realizations of these, but really what are estimated are these gammas. That is what is estimated. And so this mixed model is what is estimated by all the multi-level packages. Although there, are a couple packages like MLWin and HLM packages that will show you the level 1, level 2 representation of the model. Okay. But even in those packages, really what's being modeled is actually this equation right here. So I should note that U0J and U1J, those are between person random effects. And there's a distribution of these. There's one for every person J. And so basically this itself is a variable, if you could think about it, because it varies from person to person. And so is this. This is allowing the intercepts to be different for each person. This is allowing the slopes to potentially be different for each person. And so those terms, those between person random effects, okay, we can construct, or what is also part of the multi-level model is a variance covariance matrix of these between person random effects. That variance covariance matrix is often called tau. That's often what it's called, capital T tau. And lowercase tau represents the elements of the tau matrix. So tau 0, 0 represents the variance, the between person variance of the intercept random effect. Tau 1, 1 represents the between person variance of the slope random effect. And then tau 1, 0 is the covariance between the between person effect for the intercept and the between person random effect for the slope. It's a covariance. And this is a diagonal matrix, so tau 1, 0 and tau 0, 1 are equivalent. Okay, so this is a symmetrical matrix. Okay. But these turn out to be additional parameters that are estimated by the model. So basically, there's going to be 1, 2, 3, 4, 5, 6, 7 gammas. There's going to be a variance for the, I'll go down here, a variance for the E sub ij's, which is called sigma squared. And then there's going to be a variance for U0j, variance of the intercepts, variance of the slope, U1j's, and a covariance between these two. So those are the parameters that are going to be estimated. A couple of words about the within person random effects. So the within person random effects, the EIJs, they capture unexplained daily variability and intimacy. You could think of them as residuals, or you could think of that term representing all the unmodeled and omitted effects that could be having an influence on daily intimacy, but that we have not included in our model. Okay, so that's another way of thinking about residual. The variance of this residual is called sigma squared. So the variance of this residual term, or those residuals, is sigma squared. Typically, the errors, these within person errors or residual, are assumed to be normally distributed with a mean of 0 and a variance of sigma squared. We'll talk a little bit more about some other assumptions about the errors, like, for example, they're not autocorrelated. they're independent of each other, like they are normally distributed, which is what's said, which is what's said here. A more complex version of the residual term can have autocorrelation built into it, and it would look like this. So EIJ, the E sub ij's, would essentially be indexed by a row term. There would be a row parameter picking up autocorrelation between adjacent error terms. So the error at time t minus 1, or I minus 1 in this case, and the error at time I. And so the degree to which there is an association there, that residual, that association will be captured by a row parameter. And then new IJ here would be the within person random effect purged of autocorrelation, because it's being picked up by the row term, the autocorrelation. And this is lag 1 autocorrelation. In theory, you can also have lag 2, lag 3, if you wish. But lag 1 is usually at least what should be included in these kinds of models based on intensive longitudinal data. Okay. Here's a spaghetti plot. So before we actually look at the results and look at the actual coefficients, the estimates, the inferences about those estimates, here is a plot that basically tells the story of the findings. And I think it's useful to be able to see the story first before we jump into looking at the numbers, because this plot is based actually on the estimates. But this, I believe, is a great way of depicting what's going on in this kind of design, or at least in terms of the analyses of the data that come from this design. So on the x-axis is daily conflict. These are the days that are 0 or days that are 1, okay? And intimacy is on the y-axis, ranging from 0 to about 10. And this panel represents the women in the low quality relationships. These are the women in high quality relationships. One thing to point out is that there are more women in the high quality relationship, which is why there's more of these thin spaghetti as part of the spaghetti plot in this panel versus this panel. Okay, so what's going on here? Well, here we're looking at what happens when you go from a typical, let's look at the thick spaghetti, which I've been told in Italian, it's really spaghetto. Multiple spaghetti and one spaghetto. So let's look at this thick spaghetto here. And what it's indicating is for the typical woman in a low quality relationship, what happens when you go from a no conflict day to a conflict day? What happens to intimacy? We can see that it goes down some amount. Maybe it's about 2 units. It's hard to tell exactly from this, but it goes down some amount when you go from a no conflict day to a conflict day. And this represents a within person effect. And it's the typical within person effect for the low relationship quality group. Now let's look at the corresponding spaghetto for the high quality relationship group. So when the typical woman in the high quality relationship group goes from a no conflict day to a conflict day, Intimacy also goes down, but it doesn't go down nearly as much as it does for the low quality relationship group. So it goes down somewhat. Now, we don't know if this decrease is significant because we haven't looked at the inferences. We don't know if this difference between this slope and this slope is significant because we haven't looked at the inferences. But the general story that we're seeing here is that on average, there seems to be a larger decrease when you go from a no conflict day to a conflict day for women in the low quality relationship than in the high quality relationship, which lends some support for the hypothesis that relationship quality could be buffering the effects of daily conflict on intimacy, could be buffering conflict reactivity. Okay. Now, if we stop there, that would only be focusing on the fixed effects, but that's only really half the story. Because while we see these average effects for the two groups, the thin spaghetti represent the individual specific effects for each woman, right? Each woman is allowed to vary in terms of the intercept, which is the level of this line. Each woman can differ in terms of the level. And each woman can also differ in terms of the slope. So some women are going down much more quickly than the typical low quality relationship women. Some women are actually somewhat flat, and some women are actually slightly increasing. Okay? And we see a similar pattern here. Within the high quality relationship group, women are differing in their level of intimacy, but they're also differing in the effect of conflict on intimacy. So some women, their effects are much sharper in terms of the decrease in intimacy. Some women are flat, like this woman here, and some women are actually going up, like this woman here or these two women here. Now, I should mention that these lines, these individual specific lines for these women, these regression lines for these women, these come from the multi-level model. And in particular, it comes from estimating the variance of U0J and the variance of U1J. It comes from estimating these variances. And then what we do is we ask the model to essentially give us, based on those variances, give us the best guess of what the specific intercept and slope would be for each of these women and for each of these women. And then we just plot them. And that's how we get the thin spaghetti. So the fact that there's more variability that's unexplained in the intercepts, as we see here, and variability in the slopes, as we see here, suggests that there could be other, or there are other variables, other effects that explain that variability that we have not yet included in our model. And that would be above and beyond relationship quality. Okay, here's a table. And this table is an APA format. This is an example of what we would recommend being reported for results of this kind, data of this kind. Here are the fixed effects. And it's T values where the degrees of freedom, as you can see down here in the table, are based on 66 rather than the total number of observations. Okay. P values, as noted here in B, they're two-tailed, except for variances, which are down here. Intercept variance, slope variance. Sorry, excuse me. Those p-values are not two-tailed. They're one-tailed, and that's because variances can't be negative. And then corresponding confidence intervals. One thing to note is that these confidence intervals for the fixed effects, they're symmetrical. The confidence intervals for the variances are asymmetrical, as would be expected for parameters like a variance that has a boundary at 0. Okay, so gammas, here are the tau, the elements of the tau matrix, the unique elements of the tau matrix. And then here is the residual purged of autocorrelation. Here's the autocorrelation coefficient, which is essentially 0. And it's negative, which you don't see very often, but it's also not different from 0. But if it were negative, if it were substantially sized and negative, what that would indicate is instead of an undulating pattern that we saw with the residuals, it would be a sawtooth pattern, up and down, up and down, up and down. If one residual is above the line at one time point, the next one it's going to be below the line, and the next one it's going to be above the line, and so on. Okay. We'll get into the interpretation of this in a little bit, but I just wanted to show you big picture what would go into a table that you could use to represent these findings in a write-up for publication purposes, and in particular in APA format. Here's some syntax from SPSS. This model can be estimated using SPSS and using its mixed procedure here. I don't want to spend a lot of time on the syntax, other than to say that notice that the fixed effects are exactly the gamma terms from the equation. Okay. And we're going to estimate a random intercept and a random within-person conflict slope. Okay. We're telling the syntax or that the subject is the ID, and we're going to estimate all the elements of the tau matrix, which in SPSS is called the G matrix, but it refers to the same thing, the variance covariance matrix of the between person random effects. The repeated line is where we specify basically the autocorrelated residual term. And in the book website, there's actually a data file that has this syntax, as well as syntax for plotting, doing the panel plots and doing the spaghetti plot for this model. Again, intensivelongitudinal.com. Here are the fixed effects from SPSS. These are exactly the effects that are in this table. Okay. One thing to notice is that SPSS does fractional degrees of freedom based on its way of calculating degrees of freedom. What we have done is we're a little more conservative and we round these, or actually we don't round them, but what we do is we calculate by hand what the degrees of freedom are based on 66. Okay. Here are the random effects. Okay. Variance of the intercept, variance of the slopes. We'll go into interpreting these in just a little bit. Covariance of the intercepts and slopes. Here is the residual, lower level residual purge of autocorrelation. Here's the autocorrelation coefficient. This G matrix is essentially these terms right here, placed in a matrix format. This figure here is a way of depicting basically the individual spaghetti, but having the individual spaghetti plotted on top of the actual data points for each woman. So the x-axis is conflict, again, 0 days, 1 days, no conflict days, conflict days, intimacy on the y-axis. Okay. You'll notice here that, and they're ordered, by the way, in terms of most negative to most positive in terms of the slope. So you can see here again, most negative to most positive. And the reason that is done like that is so that you can see the degree of variability that exists within the low relation quality group and the high relation quality group in the slope. And while the average slope is negative for both of these groups, there are particular women for whom the effect is even positive. Well, it's more negative than the average, but also for some women, the effect is positive, suggesting that on days where there are conflicts, intimacy is higher. So perhaps for these women, conflict is a window to intimacy, perhaps. Whereas for the majority of women, conflict is associated with less intimacy. Notice also that for the women who have no conflict days, there's no line. However, there is actually an estimate. There is an estimate of what that woman's effective conflict would be were she to have a conflict. And that is the case also for the other women in the low relationship quality group. You might ask, how is that the case? That if there's no conflicts, how can the model come up with an estimate of what the conflict would be? Well, this is an example of multi-level modeling and borrowing strength. Essentially, what happens is this woman's estimate is going to be very much like the estimate for the typical low relationship quality woman. And the women who are missing in the high relationship quality group, their estimates, which are all about a -1 or so, that is very similar, and it's going to draw very heavily from the effect for the entire high relationship quality group, which we'll see and interpret very soon. Here's another plot, just again, trying to show you, this would be too much for a publication, but we might imagine as a way of showing how much variability there is. This is a plot that's basically showing, quintiles, the lower 20%, the next 20%, the middle 20%, the next higher 20%, the highest 20%, just representative trajectory or representative woman for each of those quintiles for the low quality relationship and the high quality relationship. And of course, notice that the confidence limits for the effects are much broader when there's only one conflict. But when there are more than one conflict, you can see that the model says that it can do a much better job at estimating what the individual specific line is for that woman. Here is syntax to reproduce this example in M+, which is started as a structural equation modeling program, but over time morphed into a multi-level structural equation modeling package. And so you can do multi-level modeling in M+. Here's the syntax for doing that. This is not a class on syntax per se, but the important thing to notice is that we're including the same variables, of course. We have to declare what variables vary only within person, which variables vary between person, and then the ones that are on neither line are the variables that vary both within and between person, which essentially is our outcome intimacy. Okay. So this, again, on the website for the book is called process.inp, chapter 5. Here's a comparison of the SPSS mix and M+ syntax. Okay. For ease, and because there was no autocorrelation effect, we're making the comparison of the two without any residual autocorrelation. And the thing to notice is that the fixed effects are essentially bang on, pretty much exactly out to 3 decimal places. Where you may see some slight differences would be in the between person random effects, but even those are very closely estimated. They're very similar in their estimation. The within person variance is usually very, very similar, and they are the same within rounding. So we're getting the same results here. One thing to notice in M plus is that M plus assumes larger sample sizes. So what it does is it gives you a z-test, the ratio between the estimate and the standard error in the form of a z-test and an associated p-value, which means that there's no degrees of freedom like there would be for t-tests. But of course, with large sample sizes, t and z essentially converge to the same p-value. This slide is just depicting a portion of a write-up in chapter 5 of our book for this example, showing you how we might write the results up of this example in APA format, including some figures and including the table that we showed earlier. So if you want to see an example of how this might be written up and explained to an audience, you can check that out. Now let's just take a moment to interpret the fixed effects, and we're going to focus primarily on the important fixed effect, which is going to be the within-person effect of conflict and the cross-level interaction in particular, which is the one that tests the buffering hypothesis. So here it is. This is the buffering hypothesis. The coefficient is 1.02. And as said here, this estimates the number of units different in the slope, in the within-person slope, between the high-quality relationship and the low-quality relationship women. And essentially what this says is that women in high-quality relationships are 1 unit less reactive in terms of the intimacy scale, in terms of a difference between no conflict days and conflict days. Right? So that's what basically this says here. That effect is statistically significant at the 0.05 level. But more importantly, it's a 1 unit difference in the within-person slope, 1 unit larger or higher in the slope indexing the basically conflict reactivity when you go from a no conflict day to a conflict day in terms of the change in intimacy. So this is the cross-level interaction. The next slide essentially shows you how to make sense of the effect for the low relationship quality women, which is about -2 units. Right, so it's -2 units for the low relationship quality women in terms of when you go from a no conflict day to a conflict day for the typical low relationship quality woman. But then the difference is 1 unit between the high relationship quality women and the low relationship quality women in terms of that effect, which means that the slope for the high relationship quality women is -2 plus 1, which essentially is -1 or -0.99, but rounding and among friends, it's -1. So basically, the slope for the low relationship quality group is -2. The slope for the high relationship quality group is -1, the within-person slope indexing the relationship between daily intimacy and, daily conflict and daily intimacy. So basically, it's about half for the high relationship quality group than the low relationship quality group. But again, that's only half the story, focusing on the fixed effects. It's also important to focus on the random effects. And let's make sense of the random effect for these slopes here, right? This is a slope for the low relation of quality group. And the slope for the high relation of quality group is 1 unit lower, which means that they're a -1. Okay. Oh, and by the way, I didn't point out that the effect for the low relation of quality group of the 2-unit decrease due to daily conflict is statistically significant. But to make sense of the variability that is the thin spaghetti, we need to take a look at the random effect for that within conflict slope. That random effect is 2.71. 2.71. Now that is in variance units. To really understand what's going on, it's best to take the square root of this. And the square root of 2.7 is 1.6. And the random effects are assumed to have a normal distribution, which is why if we take the square root, we get a standard deviation. And we can actually have plus or minus 2 of those standard deviations to create essentially a prediction interval of where approximately 95% of the slopes in the population fall. So basically, it would be between plus or minus 3.2 units around this -2 coefficient is where approximately 95% of the slopes would be expected to be found in the population. So that suggests that for some women, the effect of conflict is over twice as large, because if you take -2 and subtract -3.2, you get -5.2. But for some women, this association is actually positive, because if you take -2 and you add 3.2, you get about 1.2, indicating that for some women, the association is, more conflict is associated with more intimacy, although the average effect is negative. Okay. But this gives you an idea of how to understand the individual differences of the between person heterogeneity in this effect. Okay. And we can do the same exercise also for the high relationship quality women. Okay, keeping an eye on the time, we wanted to keep each part to about an hour and a half or so. So I'll keep moving along. Let's talk a moment about model assumptions. Many of the assumptions for the multi-level model are similar to the ones for regression. Linearity in the relationships between the predictors and the outcomes. Normality in the errors, and which essentially means if it's a continuous outcome, normality in the outcome. Independent, IID, independent and identically distributed errors. So no order correlation in the errors. Another one that comes from multiple regression is that the residuals are uncorrelated with any of the covariates. And this one, consideration of confounders, is particularly important when we're trying to make causal inferences, especially with observational data. It's important to take into account confounders of the, in this case, daily conflict and daily intimacy relationship, the within person X and within person Y relationship, or the within person relationship of X and Y. One thing that we mentioned earlier is that any and all between person variables cannot be a confounder of the within person relationship of X and Y. And that's because between person variables only contain between person variability, so they cannot be alternative explanations for why the within person variability in X is associated with the within person variability in Y. Okay. That's one nice feature of the within person effect in multi-level models. We also controlled for time. So time is a natural potential confounder or alternative explanation for why time varying X would be associated with a time varying Y. And so we've controlled for that in the model. So that is another confounder that we've taken into account. And we could have also thought about and considered and eventually entered other confounders that are time varying. So while time invariant predictors cannot be confounders of the within person relationship of X and Y, there can be potential within person X's or within person third variables that could confound, or that could be alternative explanations for the link between X and Y. But a degree to which you consider confounders allows you to, or lends credence to causal inference. Another assumption that comes in particular with intensive longitudinal data is the stationarity assumption. And this is an assumption that you might have heard of, and it comes from time series literature, where there are often a lot of repeated measurements on a particular unit, like the stock market, for example, some index in the stock market tracked over many years. The stationarity assumption basically says or assumes that the process that you're studying is stable over time. And that translates into the mean being stable over time, the variance of the outcome variable being stable over time, the covariances between the X's and the Y time varying Y's being constant over time, and the autocorrelation or the relationship between X and Y being autocorrelation in the residuals, but also the covariance or autoregression of X and Y being stable over time. Okay. So what would be some examples of non-stationary data? Well, if you have linear trends or quadratic trends over time, systematic time trends, that means that the mean is changing over time, right? So that is a form of non-stationarity that needs to be accounted for in some way. Seasonal cycles or other kinds of cycles that may take place. Remember how we talked about the example of weekend and weekday or day of the week cycles that can show up potentially depending on the variables that you're assessing on a daily basis. That would also be an example of non-stationarity. Or if there's some kind of change in variance over time, like if the variance of Y gets smaller over time or gets larger over time, that's another example of non-stationarity. Now, what are the consequences of ignoring non-stationarity? Well, essentially, ignoring non-stationarity leads to bias in the coefficients. So you want to not ignore non-stationarity. You want to somehow deal with it. If you have non-stationarity in the mean, you want to model the time trend. So if there's a time trend, you want to model that. And sometimes a version of doing this is called detrending. That is taking into account the time trend in some way. Now that's the easier one to deal with. Non-stationarity of variance or of associations between variables, that is more complex. That's more difficult. And we don't have time to go into the complexities of that, but there are some references that will go into that for you. Now, in the absence of a measured variable that predicts non-stationarity features reasonably well, here are some options to deal with non-stationarity. So there are some models for exploring the nature of the non-stationarity, forms of spectral analysis from the time series literature, time varying effects is also another one, where the relationship between X and Y itself is modeled and over time in terms of it changing over time. You can also look for or try extensions of models where basically introducing an abrupt change. Sometimes these are called regime switching models. There's an example in the reference for that. Moving average models are another way of taking into account non-stationarity. Sometimes you can transform your data to reduce the amount of non-stationarity. That is an option that can be considered at times. Another thing is that you can ultimately try to turn back to theory or collect more data to try to understand the dynamics of the process that you're examining that contains non-stationarity, to try to get a better idea of where the non-stationarity or what it's due to. Let's talk a minute about intensive longitudinal data with cycles. So intensive longitudinal data can be very well suited for modeling cycles in some process over time. So here are some examples. So postprandial, which is basically after a meal, if you wanted to look at the change in glucose before versus after a meal, after meals, well, there are going to be cycles related to the meals then, because people's glucose go up and then go back down over a period of time in relation to, meal intake. Diurnal rhythms, so cortisol shows a cycle. If you were to measure cortisol continuously throughout the day over a number of days, you would see that it follows a rhythm or a cycle. Okay, and you'd want to make sure that you capture that cycle if you're going to do modeling of cortisol data, if you've measured it continuously. Weekday, weekend effects that we talked about. So mood often, or momentary affect, or mood often shows these weekday, weekend effects. Basically, moods are more positive, less negative on the weekends than they are on the weekdays. Should be no surprise. But that's going to show up as a cycle if you were to measure continuously over some days, over multiple weeks, mood. And you want to take that into account. Seasonal effects, if your data stream is long enough over time, and the thing that you're modeling has some kind of change due to the season or due to the month, like you see in some econometrics examples, that's another example of cycles. Now, these are all also examples of non-stationarity. So you're going to want to model cycles whenever possible. And the way to determine whether you have a cycle is, one, your understanding of the phenomenon. So you have to have some, theoretical understanding of the phenomenon that you're trying to study. And you can also plot your data, right, using these, what I showed you as panel plots. You should be able to see with your eye also evidence of some cycle when you plot the raw data. So these cycles should be modeled explicitly. You could do this by essentially residualizing out the cycles, possibly. That's one option. Or you can include the cycle as part of the broader analysis of intensive longitudinal data. Another issue with longitudinal data generally, and certainly it's a case with intensive longitudinal data, are missing data, right? Now, there are courses and books on missing data, so we're not going to be able to go into a lot of detail here. But there are a few points that are worth making. One is that the maximum likelihood estimation approach that's reflected in multi-level modeling can accommodate missing data, assuming that the data are missing at random. Now, missing at random data basically means that your data are missing in an ignorable way, conditional on the X's that you have in your model. So basically, you have predictors in your model. They can be the substantive predictors, or they can be non-substantive predictors, but that are related to missingness. And those are often called auxiliary variables. But the idea is that your collection of X's are related to Y such that it allows you to make the assumption that the data are missing in an ignorable way, conditional on your collection of X's. A way to bolster the MAR assumption is to include variables in your model that are either predictive of missingness, and that would be of missingness in the either at the, well, really it would be the within person, your outcome, Y, that varies within person and between person, but the within person variability, if there's missing data at that level, you would want X's that also vary within person and that are correlated with Y. And hopefully the X's don't have a lot of missing, because maximum likelihood estimation for dealing with missing data is about missing Y's conditional on observed X or X's. You can also include X's that are related to the Y. So they may not be predictive of missingness, but they may be related to the Y variable that has missing data. So to the degree to which you can include those auxiliary variables in your model, that would bolster the MAR assumption. Okay. Now, what this also means is that if you're missing predictor variables, if you're missing a predictor variable on a particular day, that entire row is going to be dropped. So the row is going to be that, in this case, particular time point in our example of 28 days. If you're missing an X, that row is going to be dropped. Okay. In growth curve modeling, it's not as big of a deal because your key predictor is time. And if you are missing a Y, but you know that it was missing at a particular time point, you're good. However, in this situation, if you're mixing an X, Y in the standard multi-level model, Y will be dropped for that row that also has the missing X. Okay. possible way around that is if you treated X instead of fixed, you treated your X as random, which basically means that you bring in information about the mean and the variance of X into the model, which is essentially converting your X's into outcomes, but outcome variables that have no predictors. And that can be an option, especially if those predictors are continuous. And again, this is all based on the MAR assumption. So the degree to which you can include, predictors of the missingness on the X's, that would bolster the assumption. Another option is multiple imputation, which I don't want to get into in a lot of, we don't have time to get into here, but it is another option to be considered. It's a principled approach to dealing with missing data, where you have an imputation model, and then you also have a broader model that contains also auxiliary variables, again, to bolster the MAR assumption. Another issue with intensive longitudinal data that often comes up is having unequal sampling intervals. So an example of this would be experience sampling experience sampling methods, or ecological momentary assessment, where there are random signals that are delivered throughout the day, sometimes within blocks, but they're random. And then that will lead to a situation where everybody may have the same number of signals, but the signals happen at different times for different people. And in that kind of situation, that can present some challenges. And it kind of highlights the difference between multi-level modeling and time series modeling. Okay, so in multi-level modeling, if you're not interested in any kind of lagged effect, basically you're looking at concurrent associations between X and Y, which is actually what we did in the example that we looked at earlier, then that concurrent effect, there's no problem with that. There are no assumptions that are being violated, even if you have unequal intervals between the time points, and that those intervals vary from person to person. They're different for different people. Okay. Time series, where you're often interested in either autocorrelation or autoregression, that is lagged effects, that's where time series explicitly makes the assumption, and has to make the assumption, that the intervals between the assessments are equal. Right? Because basically, if you're looking at autocorrelation in the residuals, or autoregression, where it's the lagged outcome variable predicting the current value of the outcome variable, if the lags are varying, basically the sampling intervals are varying depending on the time point, then a single coefficient is not going to be able to capture what that association is, right? So basically comes down to, if you're interested in concurrent associations, there's no problems having unequal intervals and equal sampling intervals. But if you're interested in lagged associations, there you will have to do something to be able to account for the fact that the sampling is leading to unequal intervals. Okay. And essentially, one way of handling that is to create equivalent bins. So you create bins of time that are equivalent. Let's say a 2.5 hour bin, and you have multiple 2.5 hour bins going across the entire day. And what you do is you place the particular signal that leads to a repeated measurement. You place that measurement into the particular bin that it should fall into. Right? And so what that creates then is a situation where, because the bins are equal and you drop the assessment into the particular bin that it falls into, then you're going to have equivalent intervals. You're going to have equal intervals. However, that's going to lead to a situation where you're going to have missing data, right? They're going to be missing, there are going to be some intervals that won't have a sample, okay? Or that won't have a signal that falls into it. So they're going to be missing data for potentially for each person, but then it becomes a missing data problem from an estimation perspective. And you create the equivalent intervals. And while some people may not have data in interval 2 or 5 or 7, there are going to be other people who do have data in intervals 2 and 5 or 7. And basically, you'll be able to still estimate a within-person effect based on everybody's data, even though there are going to be some missing outcomes for some particular people, in particular bins. So that's one way of handling unequal sampling. And M+, for example, actually automates that process for you with an option called T-interval. And there's a paper in the references by McNeish and Hamaker that explains how the T-interval works to create these equal intervals. The other option will take you out of this modeling framework, which I haven't described this yet, but it's a discrete time modeling framework. It's going to take you out of that framework and into a continuous time modeling framework, where time is treated continuously. And in that context, it turns out that unequal intervals are not a problem for continuous time models. But continuous time models are really a different animal from the kind of modeling that we've been doing here. And again, that's a much more advanced topic where I've provided some references for people who are interested in learning more about that. So here are a few modeling extensions of the multi-level model, okay? First is analyzing multiple time series. So let's say you're interested in modeling autoregressive effects and or autocorrelated effects, and you have a lot of time points. Initially, time series was developed for N of 1 situations in econometrics, but what if you have many more units than just one, but you're wanting to essentially pool effects across the individual time series for each person? So there is a version of structural equation modeling called dynamic structural equation modeling, or DSEM, or residual dynamical structural equation modeling. And this is implemented in M+, but there are also some R packages that are available to do this kind of, essentially what might be called multi-level autoregressive time series modeling. Another extension that I had mentioned earlier that deals with the unequal intervals is continuous time modeling. Okay? Basically, it models the process in terms of the association between X and Y in a way that's independent of the time lag. While this is a great model for those kinds of data with unequal intervals, it's a complex implementation. So for example, there are versions of this that involve estimating differential equations as a way of being able to do continuous time modeling, and it often requires specialized software, but it is possible. Some other interesting extensions could be multi-level modeling of variance heterogeneity, essentially allowing the residual variance to vary from person to person. So basically, we were assuming that the residual variance for each person, the ups and downs for each person, the variance of those ups and downs were the same from person to person. That was an assumption that was being made in the multi-level model that we were talking about and going through. But what if people vary? What if some people have much bigger variances, within person variance versus smaller within person variances? That would have to be reflected in a model where you allow the sigma squared to vary from person to person, essentially allowing each person to have their own sigma squared. And then you can predict the between person heterogeneity in the sigma squared using person level predictors. M plus is a package that allows you to do that kind of modeling. And a biostatistician named Don Hedeker also has specialized software to do this kind of modeling. And he calls it location scale modeling, where location refers to variability in the mean level of an outcome, and scale is variability in the variance of the outcome. Another model extension is to incorporate measurement error, right? So measurement error can create bias in parameter estimates, can also create bias in standard errors. And that's because of having unreliable measures of predictors and or outcomes. And so an extension of the multi-level model that we examined would be multi-level structural equation modeling, where essentially we can have a y that where variability is at different levels, but there's a measurement model placed on y, and there can also be a measurement model placed on x within the context of a multi-level model. Okay, so that's a very interesting extension that where people are doing work on that. And if you also want to include, if you want to have models that have multiple outcomes, again, that's another context where multi-level SEM, multi-level SEM would be the thing to turn to. And then if you're interested in doing the lagged effects of that kind of, modeling lagged effects essentially, but of multiple outcomes at the same time, that would be a version of multi-level VAR modeling, vector autoregressive modeling, where basically the vector part refers to the fact that instead of having one outcome, you have a vector of outcomes that have been that are varying over time. So lots of extensions to the basic multi-level model that we've been focusing on. There are different software packages for doing multi-level modeling. Here are several of them. There are free packages like in R. These other ones are, there's a cost to them. Oh, they're all great. And for the same data set and for the same model, these will all give you the same results. Okay. For the extensions that we talked about, you need to move to more specialized models, some of which are available freely in R, and they're listed here for doing some of the extensions that were on the previous page. M Plus also does a lot of the extensions that were noted on the previous page. And the note down here is just suggesting that when, I think it's a good idea to be familiar with more than one program, because it gives you confidence in the findings, especially if you can replicate the results across packages. But it also gives you some insight into the strengths and weaknesses of the different packages, because there are some differences between the packages that are worth noting. And really the only way to understand them would be to actually take the same data set and try to model it across multiple packages. We've done some of that in our book, where you can find code for example, this process example, using SPSS mixed and SAS proc mix, as well as an LME, I believe also Stata, HLM, and M+. Okay, so other syntax, like I mentioned, for this daily conflict and intimacy process example can be found at intensivelongitudinal.com. Here are some books about intensive longitudinal data and related designs that, if you're interested in finding out more, these would be great books to get started on. I think this handbook is also particularly useful as a way of getting introduced to these kinds of designs. And finally, there are a couple pages here at the end with some references and some recommended readings that you can peruse at your leisure. So that's it. Thanks for your time. This section went about an hour and 50 minutes or so a little longer than part one, but hopefully you found this somewhat useful and give you some background to lead you into the SAMSI program that is taking place in spring 2021. Thanks very much for your time, and take care. Bye-bye.